Welcome to this talk. I'm going to talk about versatile model for design and verification of chemical products. What I'm presenting is the result of an international collaboration between two universities in China and myself in Denmark. The first thing we need to see is the relationship between product and process. What we can see is that there is a number of chemicals-based products that are needed for the sustainability of modern society, and all these products are obtained through different chemical processes. And what is the relationship between them? In order to obtain the desired products that society needs, it is necessary to select the raw material from which they can be obtained and to design processes that can manufacture them in a sustainable manner. That is, the product and the process are modeled by different sets of equations which change when the system changes, if we want to solve them on a computer-aided basis. And the different sets of submodel equations also means different problem solutions that would be needed for solving different types of product design problems. That means if we have different products, we have different processes, we have different sets of equations, we need different solution strategies. These are issues that I will highlight in this presentation. Let's look at the versatile product design model. The original model was proposed by Kai and his group from Hong Kong, and in this work we have extended the model in terms of that each of the models that you see in different colored boxes, they're not just one equation, but they are a vector or a matrix of equations. The problem is formulated as a mathematical programming model, which can be solved in different ways. The typical product design problem includes the molecular structure model, the property model, sometimes the process model. But if we want to look at the cost or the economics, we need those models. If we want to include environmental impact, sustainability, we need those models. And we'll show them in more detail later. So that's the overall versatile model. One or more of these equation sets would be needed to any design problem. And we can see a little bit more in detail here, the molecular structure. That's the valency rule, structural constraints, property. There are four kinds of property: primary property, secondary, functional, and mixture phase equilibrium type. Primary and functional, these are usually one equation per model. Secondary can be more than one equation per model. Mixture definitely is a subset of equations per property, and depending on the property model, it can be even hundreds of equations. The process also depends on the process and the model complexity. The conservation equations are there, conditional equations, defined equations, and correlations. So again, depending on the model description, it can be simple correlations, it can be a combination of all the equations. The last set of models, quality, cost, economic pricing, environmental sustainability, performance. One aspect of these models, they are usually simple correlations, but they need data or results from property and process, solution of property and process equations. The decomposition-based solution strategy is as follows. On the left-hand side, we have the functional groups, which are the building blocks, which when combined together will form the molecules. And then we have the objective function, and then we use a decomposition-based approach where after every step that is satisfying the constraints, we reduce the search space. So the highest search space is when we are forming the molecules. Then we check them for property, then we check for process constraints. Those candidates that satisfy all these constraints then are checked for the remaining set of constraints, because the remaining set of constraints needs values from the above set of constraints. And then we can include them in a final optimization, or we can just order the candidates according to the objective function to find the optimal solution. Some examples of the product design problem in terms of equations. The simple single species molecular design problem, for example, would include the valency equations, the primary property equation, which are just function of the molecular structure, the secondary, which are functions of the primary property, and sometimes the mixture equations, like in solvent, we need to calculate the solubility, then we need the P4 equations. The known parameters are the model parameters that needs to be known. The known variables are the conditions, the upper and lower bounds of the number of groups to be used, and the calculated values are the valency criteria, the property, and the other properties that you see there. This problem, the only difference from the previous one is that a quality performance model is included in here, which are functions of the properties. Otherwise, it's the same as before. This one is different because now the process model is included, and it depends on also what kind of process it is. Then the number of parameters will depend on the process, and also the conditions will change, and the calculated variables will change. But now we have a different set of equations, and also the calculation procedure will be different. And this one is another type of problem, which is the blend. That means we have liquid of different type, and we will mix them together to form a blend. And typical problems like these are gasoline, diesel, jet fuel, lubricants, et al., and others. So here the difference between the other problems is P3, which are models for mixture. That is, properties of mixture need to be calculated. So, again, but the starting point here is not molecules. It can be molecules if we need to generate candidates for molecular design, but otherwise we have a set of molecules and we find mixtures. That is, how many compounds should be in the mixture and what is their compositions to satisfy the constraints. And compared to the blend, this kind of problem is different in the sense that it's not liquids that is being mixed, it is solid, liquid, and other liquids that are mixed together to form a single liquid phase mixture. Otherwise, it's the same. So even though the type description seems to be similar, but the properties and property models are different. And here is a overall summary of the different types of models we have shown. I will highlight two things here. For example, in the CMD2 problem, it can be solved by direct optimization, decomposition, because the models are not that difficult to solve. And adding the optimization objective function in quality, we can optimize. In here, we have added the process and also the quality and objective function. This needs to be solved in the decomposition way. We have not tried the direct, and we do not think it was worth trying. And you will see why it is. It contains a lot of different types of equations, and also some other problem like the formulation problem, where two-step solution strategies are needed. Some information about the properties. Once the chemical or the mixture of chemicals is identified, the properties that needs to be calculated, one can go to the knowledge base and get the data retrieved, or go to the ProCAMD property library and get the properties calculated if they're fast and simple. But if they are computationally intensive, like using Cosmosec and then Sigma profiles, then it needs a hybrid solution approach, where for every candidate, these properties are calculated to check their feasibility. The, the framework for the architecture of ProCAMD is such that you see at the top the models and then the submodels, and these then form the templates for design of different types of products, and then the solution approach. And then the solution approach needs database and property estimations. These are then added. I'm sorry about that block that did not get removed. And then these are then included in a ProCAPD software, where you can see we can do single species formulation, functional product, devices. They all need databases, solution approaches, property models, devices, and they are all integrated in a efficient way. The application of the workflow, which is actually the template for different kinds of problems. We define the problem in step 1, and then based on the definition of the problem, we retrieve the model equations, which then define what kind of solution approach will be used. And then one can choose enumeration, one can choose optimization, both direct and decomposition. The kinds of problems we have solved more than 100 different kinds of problems, but I'm going to highlight only the crystallization based. Actually, it's not crystallization based, it's extraction, reaction, solvent. Sorry, it's put in the different one. It should be reaction solvent. So the objective function is defined in terms of yield of dimer or the energy consumption. Then the molecular structural equations are given, the properties, one equation per property. But when we come to the process model, one can see that the liquid equilibrium is embedded into the process model. The reaction model is there. The distillation model is there. These are not one equations. There are many equations in here. And then this kind of problem also requires parameters like the reaction rate constants, and number of stages and things like that. So number of stages is not a design variable here, it is fixed. Then the total number of equations was 99, number of variables 29, number of discrete variables 27, solved with Baron, and the time is given in seconds to find. And the solutions obtained, ordered in terms of increased dimer percentage and increased energy consumption, or decreasing and increasing energy consumption. So the best is the decreased consumption. Finally, in conclusion, a versatile modeling framework suitable for chemical product design has been developed and implemented in ProCAPD, together with database, extended database library of models, corresponding solution approaches. The plan is to enhance the application range of the tool through data analytics, models generated through machine learning for properties that are not currently available, as well as new classes of design templates like cosmetics, skincare, food products. To formulate realistic product design problems with appropriate models will require handling of data from different sources, checks for their consistency, uncertainty, quantification of model parameters. These also will be included. To meet challenges of functional and formulated products, which is what we want to highlight also with this kind of tool, these kind of products make up the majority of the chemical products. A multidisciplinary, multidimensional approach to integrating data from different sources, models of different types, methods of solution, etc., need to be interfaced through an efficient and flexible computer-aided framework. That's all. Thank you very much.